Bell Labs, Murray Hill, summer 1969. Up a service stair, and through a door that sticks. A PDP-7 sits idle. No budget line, no project name. Just a humming box in a too-warm attic. Ken Thompson and Dennis Ritchie know the way up. They've just stepped off the MULTICS train. A grand promise of a computer utility that grew heavier the longer they pulled. Management called time. The partnership with MIT and General Electric ended. The meeting stopped. The room went quiet. Thompson didn't. He still wanted a system he'd enjoy using, a small one. He had a distraction, a space simulation he'd written. On GE's mainframe, it ran slowly and burned money, about $75 a game. The abandoned PDP-7 looked like a way out. He fed it paper tape, learned its quirks, and rebuilt the program there. It worked, and it did more than save money. It showed that even an old, cramped machine could feel quick in the hands. Maybe a lean time-sharing system could live here too. He sketched the pieces. A hierarchical file system, little inodes to store the facts, devices exposed as files, so the same read and write calls touched terminals and disks alike. A way to create work with fork, then replace it with exec. The PDP-7 didn't have much memory, but it could juggle users if the code stayed small. In the hallways, the name started as a joke. If the failed behemoth was MULTICS, this one was UNICS, uni-plexed, rather than multi-plexed. The joke sharpened into UNICS. That summer, Thompson's wife took their toddler west to visit family. For a few weeks he had the room and the machine to himself. He wrote an editor, an assembler, a shell, and a kernel that used half the memory and left the other half for a program to run. When his family returned, the system already booted and stayed up. He later downplayed the legend. The speed of it is on the record. The work needed better hardware to grow. After MULTICS, no one upstairs would approve another operating system. The help came sideways. Bell Labs' patent department needed exacting page layouts with line numbers and special symbols. Joe Osana said he and the group could build the tools if they had a PDP-11. A PDP-11 arrived in 1970. UNICS moved. By day, clerks formatted patent filings with NR off. At night, the researchers slipped back in, careful not to jeopardize the day's work, careful to push without breaking. Results convinced people faster than memos could. A second PDP-11 showed up, dedicated to the system. In November 1971, Bell Labs issued the first edition of UNICS. The photo from the next year shows it plainly. Thompson at an ASR-33 teletype, Ritchie beside him, the PDP-11 blinking in the background. The room around the machine developed its own gravity. Whiteboards filled and were wiped. Someone kept the espresso pot going. Brian Kernighan stopped in to make a line read cleaner. Doug McElroy leaned on the table and argued for tighter tools. Osana tuned the typesetter again. The more they used the system, the more the system suggested what to do next. One afternoon, a small experiment unlocked a habit. McElroy had been pushing for years. Let programs connect like plumbing. Thompson added a system call, taught the shell the vertical bar, and chained two commands. Output from one became input to the next. It felt right immediately. Commands trimmed their chatter. Tricks turned into patterns. A calculator fed a number-to-words filter, then a speech program. Type 1, 2 plus, here 4. The room laughed, then kept going. Not bigger programs, composed ones. Another barrier fell. Dennis Ritchie's C matured from its B roots and reached for the kernel. Operating systems were supposed to live in assembly, tied to a single machine. They rewrote UNIX in C and loosened the knot. Portability turned practical. In 1974, Thompson and Ritchie described the system in Communications of the ACM. Labs outside Murray Hill could read it, build it, change it. Before we head west to Berkeley and watch UNIX spread, a quick thank you to the team making this story possible. Emergent is where a conversation with AI becomes a production-ready app. Not a mock-up, real code with backend, auth, database, payments, tests, and one-click deploy. Their multi-agent vibe coding wires up full-stack apps as you describe them, then lets you iterate in real time. Need Stripe, login, live chat, or an admin dashboard? Just say it once. There's a native backend, GitHub integration, and for power users, Pro Mode with giant context windows. Over 1 million builders are already shipping with Emergent. And just to show how it works, here's something we could spin up in minutes. Here's a quick demo. UNIX Timeline Explorer, an interactive app tracing UNIX from the PDP-7 to Linux and macOS, built in minutes, deployed to web and mobile. Emergent handles the backend database for the timeline, the interactive UI for the front end, and deployment to both web and mobile, all from a conversation. That's how powerful vibe coding really is. Check the link below, and start building today. Now back to the story. AT&T still wasn't a software seller. It licensed UNIX to universities for modest fees. The tapes came with source and no support. That absence created its own ecosystem. Students learned by editing what they had in front of them. At Berkeley, Thompson taught for a term. A graduate student, Bill Joy, tore into the code. He wrote V, a screen editor that made glass teletypes feel fast, and the C shell for interactive work. As ARPA networking gathered steam, The Computer Systems Research Group folded in TCP/IP. Berkeley's distribution, BSD, became a main line. A different text made the rounds off the record. John Lyons wrote an annotated commentary on the version 6 kernel, source code line by line with explanation. AT&T's rules kept it off bookstore shelves. Photocopiers did the rest. The grey market stacks smudged with pencil taught students how a real OS actually worked. User groups met because there was no one to call. A 1974 meeting in New York grew into newsletters, conferences, and then UNICS. Hotel rooms full of terminals and hallway arguments. Code traded across tables. If you needed help, you found the person who wrote the tool and watched them fix it. By 1979, version 7 was the Bell Labs line at its cleanest. BSD moved with new hardware. DEC's VAX brought a roomy 32-bit address space. Berkeley wired in virtual memory. Networking and job control matured. Sun built workstations on BSD. DEC shipped ULTRICS. Next took the tree in its own direction. The current split but stayed recognizably the same river. The Bell system breakup in 1982 changed what AT&T could do. Internal additions turned into products. System 3, then System 5. Vendors poured in. IBM shaped AIX for its servers. HP built HPUX. DEC pushed ULTRICS. Microsoft licensed the code and shipped XENIX. Briefly the most widely installed UNIX. Choices multiplied. So did differences. One camp favored sockets and the Berkeley network stack. Another leaned on System V's IPC and streams. Start scripts, libraries, header files, even command options diverged. The same program built 3 ways in 3 shops. Standards bodies tried to pull it together. The System 5 interface definition laid out calls and behavior. IE's POSIX drew a portable baseline. Xopen bundled APIs and built certification around the name UNIX. Alliances formed. Sun and AT&T joined to push UNIX International. IBM, HP and DEC backed the Open Software Foundation. Press events and position papers sketched incompatible futures. Inside customer sites, administrators stacked binders and tried to make them line up. Then came a lawsuit. AT&T's Unix system laboratories sued the University of California and BSDI, saying Berkeley's code still included proprietary AT&T material. For years the question shadowed purchases and lab decisions. In 1994, the settlement made the BSD line clear and legal. The open path survived. The chance at a single commercial Unix did not. Inside the kernel, the rules were still simple. Names in directories, facts in inodes, devices as files, processes created with fork and replaced with exec, standard input and output tying programs together, pipes carrying streams, signals tapping a process on the shoulder, daemons staying up when no one else wanted to, sockets letting the same read-write, ideas cross the network, a shell doing the wiring with plain text. Small tools won. When a tool grew swollen, someone split it and joined the halves with a pipe. By the early 1990s, the shape was familiar beyond ownership. GNU had recreated most userland tools under free licenses. In August 1991, Linus Torvalds posted about a hobby kernel for 386 PCs. Volunteers arrived. GNU tools fit around it. Distributions formed. Slackware kept things close to the metal. Debian organized a community's work. Red Hat focused on installable, supportable systems. On the other bank, BSD returned as FreeBSD, NetBSD and OpenBSD, each with clear goals. The internet needed what Berkeley had refined. The TCP/IP stack that began as code on campus machines ran across backbones and under early web servers. Daemons that once taught students inter-process communication became the processes that kept the network lit. Vendors refined their lines. Sun turned Sun OS into Solaris. IBM kept AIX on a tight path. HP hardened HPUX. Next work moved into Apple. Darwin, with a hybrid XNU kernel marrying Mac ideas and BSD code, sat under macOS and later under iOS and the rest of Apple's platforms. Another legal fight rolled in from a different angle. In 2003, ESCO claimed Linux contained stolen Unix code, sued IBM and Novell, and sent letters that spooked customers. Conferences filled with talk about ownership rather than syscalls. Courts examined claims over years. The major theories fell apart. The worry took longer to fade than the filings. By then, Linux was already standard in server rooms and soon in clouds. Meanwhile, the systems multiplied in places that don't advertise themselves. Linus ran on clusters and supercomputers. Android carried a Linux kernel into billions of pockets. BSD sat inside firewalls and storage appliances and routers. Televisions, cameras, cars, and base stations booted something Unix-like and went about their day. At Bell Labs, the original crew looked past the horizon. Plan 9 treated everything as a file, including remote services, and made namespaces a first-class tool. Some of that thinking, like proc and per-process views, showed up elsewhere years later. Inferno pushed distributed ideas further. These systems didn't replace Unix, they cleared space for new questions. Licenses shaped how code traveled. BSD's permissive grant, let companies take code private and ship products. The GNU General Public License required that changes stay shareable under the same terms. Projects chose lanes. Arguments about philosophy flared. The software kept moving. Standards work landed where it mattered. POSIX gave a ground most systems could stand on. The single UNIX specification, stewarded by the open group, turned UNIX into something you certifiably were or weren't. Some systems wore the badge, others didn't. At a prompt, the same shell waited for a command. People moved on and kept working. Thompson and Ritchie accepted awards they had earned years earlier and went back to code. McElroy kept offering ideas shaved to the line. Kernighan wrote so others could see what he saw. Students who had stayed up with taped-together manuals founded companies and sat on standards committees. The jokes traveled, so did the habits. Plain text if you can, compose tools when it helps, keep interfaces small enough to fit in your head. A day in the Unix room would not have looked dramatic. Someone debugging a driver, someone else arguing over the best way to list a directory, coffee rings on the desk, a visitor listening to an argument about signals, then going back downstairs with a new trick. That sound hasn't changed much. A laptop wakes and the scheduler decides who runs. A phone starts a service and binds a socket. A container spins up a process tree that would look familiar on a PDP-11 printout. One command's output becomes another's input with a single character. A log line rolls by that wouldn't surprise anyone in that attic. There's that photograph. Teletype, 2 engineers, a mini-computer, no ceremony, just work. But the shape on that desk, commands chained, files named, processes breathing in and out, traveled a long way. The attic at Murray Hill is quiet now. The pattern isn't. It lives in workstations and servers, in phones and sensors, in racks humming behind glass. It crosses oceans in fiber and rides the air on radios. It sits in lectures, in basements, in control rooms and traffic lights. Open an app. A process forks and execs. Fetch a page. A socket opens and bytes move. Pipe 2 programs together and watch a new tool appear in the line between them. The same ideas keep doing their jobs. That PDP-7 was supposed to be scrap. 2 people pulled up chairs. The rest followed.